This video lecture explains about mutual exclusion in distributed systems. So on the completion of this video, the students will be able to understanding the approaches for implementing distributed mutual exclusion and the requirements of mutual exclusion algorithms and the performance matrices. Next we see about what is meant by distributed mutual exclusion. So mutual exclusion is a fundamental problem in distributed computing systems. Mutual exclusion in a distributed system states that only one process is allowed to execute the critical section at any given time. It is the requirement that a process cannot access a shared resource while another concurrent process is currently present or executing the same resource. So the mutual exclusion is a concurrency control property which is introduced to prevent the race condition. Race condition means when at least two threads are accessing a variable and one of them writes the value while another is reading. In such a case, the result of operation will vary depending on the arbitrary ordering of threads. In a distributed system, shared variables or local kernel cannot be used to implement the mutual exclusion. The only way is message passing. So the message passing is the only way for implementing the distributed mutual exclusion. The decision as to which process is allowed access to the critical section next is arrived at by message passing, in which each process learns about the state of all other processes in some consistent way. So the design of distributed mutual exclusion algorithm is complex because these algorithms have a deal with unpredictable message delays and incomplete knowledge of the system state. For this purpose, we are using three basic approaches for implementing distributed mutual exclusion. The approaches are token-based approach, non-token based approach and quorum-based approach. First see about what is meant by token-based approach. A unique token is shared among all the sites in this approach. If a site has a unique token, it is allowed to enter into the critical section and it continues to hold the token until the execution of the critical section is over. This approach uses the sequence number to order the request for the critical section. Each request for the critical section contains a sequence number. This sequence number is used to differentiate the old and current request. This approach ensures mutual exclusion as the token is unique. The example of this approach is Suzuki-Kasami broadcast algorithm. Next approach is non-token based approach. In this approach, a site communicates with other sites in order to determine which site should execute the critical section next. In this approach, uses the timestamp instead of sequence number to order the request for the critical section. Whenever a site makes a request for critical section, it gets the timestamp. The timestamp is used to resolve any conflict between the critical section request. So all the algorithm which follows non-token based approach maintains a logical clock. The example of this approach is algorithms are Lambert's algorithm, Richard Agrawala algorithm. The third approach is quorum based approach. In this quorum based approach, each site requests permission to execute the critical section from the subset of sites. The subset of sites is called as quorum. The quorums are formed in such a way that when two sites concurrently request access to the critical section, at least one site receives both the request, and this site is responsible to make sure that only one request execute the critical section at any time. So this common site is responsible to ensure the critical section. Makava algorithm is an example for quorum based approach. Next we see about the preliminaries. So a system consists of n site means the sites are indicated as S1, S2 up to Sn. The process in this site is denoted by Pi. All the processes communicate asynchronously over the communication network. So a process wishing to enter into the critical section request all the other or a subset of processes by sending the request message. So by the use of request message, they will send the request to enter into the critical section and waits for appropriate replies before entering the critical section. A site can be one of the following three states, that is requesting the critical section, executing the critical section, and neither requesting nor executing the critical section. So in the requesting the critical section state, the site is blocked and cannot make the further request for the critical section. So during the execution, a site can enter into the site is executing into the critical section. So a site can also be in the state where a site holding the token is executing outside the critical section. Such a state is referred to as idle token state. At any instant, a site may have several pending requests for critical section. A site queues up the three requests and serves them one at a time. Next, we see about the requirements of mutual exclusion algorithm. We have three requirements: safety property, liveness property, and fairness property. First one is safety property. Safety property means at any instant only one process can execute the critical section. So this is the essential property of a mutual exclusion algorithm. So second property is liveness property. This property states that absence of deadlock and starvation. That means two or more sites should not endlessly wait for messages that will never arrive. So in addition, a site must not wait indefinitely to execute the critical section while other sites are repeatedly executing the critical section. That is, every requesting site should get an opportunity to execute the critical section in a particular time. The third requirement is fairness. Fairness means in the context of mutual exclusion means that each process gets a fair chance to execute the critical section. So in mutual exclusion algorithms, the fairness property generally means that the critical section execution requests are executed in order of their arrival in the system. So these are the requirements of mutual exclusion algorithms. Next, see about the performance matrices. Performance matrices are message complexity, synchronization delay, response time, and system throughput. First one is message complexity. That means this is the number of messages that are required per critical section execution by a state. Next one is synchronization delay. Synchronization delay means after a site leaves from the critical section, it is the time required and before the next site enter into the critical section. Normally one or more sequential message exchanges may be required after a site exit the critical section and before the next site can enter into the critical section. Next, third one is response time. So this is the time interval a request wait for its section execution to be over after its request messages have been sent out. Thus, response time does not include the time a request wait at a site before its request messages have been sent out. Last matrix is system throughput, which is calculated by using the formula 1 by SD plus E. Thus, that means this is the rate at which the system executes the request for the critical section. That is, SD is the synchronization delay and E is the average critical section execution time. Next, the performance of this mutual exclusion. That is, the best value of the response time is the round trip message delay plus the critical section time. That means 2T plus E. So these are the possible questions in these topics, that are, what are the approaches for implementing the distributed mutual exclusion, and what are the possible states for a site, and also given example algorithm for quorum based approach, and the explain the requirements of mutual exclusion algorithms, and finally draw the performance metrics of mutual exclusion algorithms. Thank you.